Come back. Conditional statements. Let P and Q be propositions. The conditional statement P implies Q is the proposition if P, then Q. That is, if P is true, then Q is true. The conditional statement P implies Q is false when P is true and Q is false. You see, if P is true and Q is false, then P implies Q is false. Otherwise, it's true otherwise, okay? So if P is true, Q is true. If P is false, Q could be anybody. So what's the point? P implies Q is false when P is true and Q is false. All right. In the conditional statement P implies Q, P is called the hypothesis or the antecedent or the premise, and Q is called the conclusion or the consequence. Hypothesis, conclusion. Antecedent, consequence. All right. Here is the truth table. So remember, if P is true and Q is false, then P implies Q is false. So if P is true and Q is false, then P implies Q is true, is false, and it's true otherwise. So that's only place when P implies Q is false. A conditional statement is also called an implication. Because conditional statements play such an essential role in mathematical reasoning, a variety of terminology is used to express P implies Q. Here are several of the many ways of expressing P implies Q. If P, then Q. If P, Q. P is sufficient for Q. Q if P. Q when P. A necessary condition for P is Q. Okay? Q unless not P. This is an interesting one. Okay? Q unless not P. P implies Q. P only if Q. A sufficient condition for Q is P. See, notice this is essentially the same as saying this. P is sufficient for Q. A sufficient condition for Q is P. Okay. What this means is the truth of P is sufficient for the truth of Q. Right? Q whenever P is true, Q is true. Q follows from P. So all these phrases mean the same thing. P implies Q. P implies Q. Okay. Here is an example. If it rains, then I will open my umbrella. So if it rains, that's P. I will open my umbrella, that is Q. You understand? Or if I receive a raise, then I will buy myself a new car. I receive a raise, that's P. I will buy myself a new car, that is Q. Note, in these cases, if I do open my umbrella, it is not necessarily true that it's raining. So notice, I opened my umbrella. Does that mean it was already raining? No. It could be because I have opened my umbrella for sun or something like that, okay? Or that I buy myself a new car does not imply I received a raise. What you can state for certain is that if my umbrella is not open, then it has not rained. Or if I have not bought myself a new car, then I have not received a raise. Suppose P is I have an identification card, and Q is I can enter this college. Express P implies Q in all of the above listed ways. What they mean is, well, you can say if P then Q. That is, if I have an identification card, comma, then I can enter this college. If I have an identification card, comma, I can enter this college. P, I have an identification card is sufficient for me to enter this college. Q if P, I can enter this college if I have an identification card. I can enter this college when I have an identification card. A necessary condition for me having an identification card is I can enter this college. You understand what I'm doing? Wherever I see P, I'm placing this statement. Wherever I see Q, I'm placing this statement. So you need to rewrite all of these in these two. Okay, so take some time, do this exercise so you have a feel for it. Okay, converse, contrapositive, and inverse. The converse of P implies Q is the proposition Q implies P. Converse means the reverse direction. For example, let P be today is a Monday and Q be I will go to the gym today. Write in English the proposition P implies Q and its converse. P implies Q is if today is a Monday, then I will go to the gym today. The converse is if I go to the gym today, then today is a Monday. Okay? The proposition and its converse do not necessarily have the truth value because you may be going to the gym on Friday, right? So the converse does not necessarily hold true. Neither do you understand. I hope one-way implication is clear to you. The contrapositive of P implies Q is a proposition not Q implies not P. Today is a Monday is P. Q is I will go to gym today. Now, so P implies Q is the following. If today is a Monday, then I will go to the gym today. Contrapositive means if I do not go, so not, if I do not go to the gym today, then today is not a Monday. You understand? The inverse of P implies Q is the proposition not P implies not Q. Notice not P implies not Q is different from not Q implies not P. Okay? So, take a moment and go through this particular exercise. Proposition and its inverse, do they have the same truth value? Take a few moments and go over this. All right. When two compound propositions always have the same truth value, we call them equivalent. So far you have seen a few compound propositions. Well, that's a compound proposition. That's a compound proposition. That's a compound proposition. Well, when two compound propositions have the same truth value, always, right? We call them equivalent. A conditional statement and its contrapositive are equivalent. The converse is not equivalent to the original. The inverse is not equivalent to the original. All right. So, contrapositive, P implies Q and not Q implies not P. These are equivalent. Okay. Converse of P implies Q is Q implies P. inverse of P implies Q is not P implies not Q. So you see, you have seen a few combinations obtained from P implies Q. Well, turns out the converse is not always equivalent, does not have the same truth value as your original one. The inverse also is not necessarily equivalent to the original, but the contrapositive is equivalent to your original one. Okay? Biconditionals. Let P and Q be propositions. The biconditional statement P double implication Q is the proposition P if and only if Q. The biconditional statement P if and only if Q is true when P and Q have the same truth values and is false otherwise. So as long as they have the same values, true here, double implication is true. False here, double implication is true. When they are different, double implication is false. Biconditional statements are also called bi-implications. So this is the truth table for a biconditional. All right. Other common ways to express P double implication or bi-implication Q are: P is necessary and sufficient for Q. If P, then Q, and conversely. P if and only if. IFF stands for if and only if Q. P by implication Q is equivalent to P implies Q and Q implies P. So that's what. This is a compound expression, proposition. This is equivalent to this.